All right, well, thanks everybody for coming. It's my pleasure to introduce Eric Coughlin, who's visiting us from Berkeley. Eric is an Einstein Fellow there, and he just 2 years ago, right, finished your PhD at Colorado, working with Mitch Bagelman, and the subject of that was tidal disruption events. Eric is specifically an expert in relativistic and radiation magnetohydrodynamics that constitute most of his work. Today he'll be talking about unfailing supernovae.
Thanks. Yeah, thanks, Luke. Thanks for having me. I apologize, I'm a little sick. My daughter just started up in daycare, and so she's like sick all the time, and then I get it. So my life has just been a revolving door of colds lately. But I'm going to try to keep coughing and sniffling to a minimum as best I can. So today I'm going to talk about a project that I worked on with Ellie Quadert, Dan Kaysen, who are both at UC Berkeley, and also Rodrigo Fernandez, who's at the University of Alberta now in Canada. He used to be at Berkeley a little while ago. And the subject is on failed supernovae, so what happens when a star reaches the onset of core collapse, but conditions just aren't right to produce a successful supernova from that core collapse mechanism, and so the star just continues to contract, forms a black hole. But what I want to talk about today is a mechanism that we think might still be responsible for giving rise to some sort of a luminous outburst, even in these failed supernovae. So these failed supernovae are really not all that failed. So just to give a summary of what I'm going to talk about today, first I just want to go over the basics, the very basics of a core collapse supernova. I'm by far not the expert in this field. This has been a topic of intense research for the last 3, almost 4 decades now, and I'm really not going to do justice to a lot of the great work that's come out of trying to understand core collapse supernovae. I just want to go over the basics because that'll set up the remainder of the talk, where I'll introduce this notion of a failed supernova, and then go through this neutrino mass loss mechanism, which is the thing that we think is responsible for giving rise to some sort of a luminous outburst, even in these failed supernovae. So I'll go through all the modeling that we've done to try to understand this, some of the applications and the results. Then I'll summarize and conclude, and I'll take any questions at the end. All right, so supernovae, how do these things work? So the idea is you have a fairly massive star, reach the point in its life where it's exhausted its supply of nuclear fuel at its core. So it's just got this incredibly dense, degenerate iron core at the center from which it can no longer extract nuclear energy. And so the cessation of nuclear burning causes a loss of pressure support in the center. That causes successive shells of material to pile onto the core. And that continues until you exceed some nuclear density threshold where you can start to produce electron-proton capture. The neutrino degeneracy pressure and also the nuclear force itself then provides some force of stabilization that halts this infall, tries to reverse it. The flow tries to come to some new equilibrium, and what tends to happen is that the protoneutron star that you form is slightly overpressured with respect to the equilibrium value that it wants to achieve. So that causes the core to bounce. That bounce then launches a shock wave that travels out through the envelope, unbinds the star, and creates a successful supernova explosion. Okay. So that's my one-page, one-slide summary of supernovae. The problem with this model is that it doesn't really work in detail. And so people realized some time ago that the shock that you form from this bounce usually stalls at pretty small radii within the star. And so the shock travels out to like a few hundred kilometers or so, and then it stalls, it just sits there. And the reason is that it's losing energy due to the dissociation of heavy elements at the shock front, and it also gets kind of stifled by the infall of the surrounding envelope that's trying to accrete onto the center. And so the shock starts to propagate out, and then it just sits there, and it doesn't really go anywhere. And this has been a huge problem since like the early 80s. And people have been working for a really long time to try to understand what revives this shock, what reaccelerates it, and what generates a successful explosion. And so one of the best leading candidates, I think, still for this is this neutrino heating mechanism. And so the neutron star is radiating a ton of neutrinos as it's forming. And so some small fraction of those neutrinos can get absorbed at the shock front, and in doing so they can deposit their energy and momentum and reaccelerate the shock that way. There are a couple of instabilities, convection and this standing accretion shock instability, or SASI. that can perhaps redistribute momentum and energy in an aspherical kind of way and allow the explosion to proceed aspherically throughout the star. Magnetic fields, of course, the cure-all for all of your astrophysical woes. They might also play a role. So Philip Mosta has done a lot of interesting work looking at how magnetorotational instability can amplify magnetic fields, drive some jet-driven supernova. That could potentially explain hyperenergetic supernovae. These are supernovae that are like 10 times more energetic than other supernovae, for which people really don't think that the neutrino eating mechanism can explain. I think the jury is still kind of out on this. I don't think there's really been a consensus established as to what actually revives this shock, what ultimately drives supernova explosions. I certainly don't know, but what we do seem to know is that certain stars are just intrinsically easier to explode than others. And so there's been a few groups now who have discovered kind of the same thing, which is that if a star has a very high degree of compactness, so this compactness parameter is kind of the ratio of the mass contained in the core to the mass immediately surrounding the core. So if that's a very high number, so the star is very dense and compact, those stars are just very difficult to blow up, right, under any of these mechanisms, really. And a number of groups have found this same result, and it seems to be true that some stars are really just too ill-prescribed at the time of core collapse to generate a successful supernova. And so that sort of prompts an interesting question, which is what happens if a star really doesn't explode? Does it just continue to collapse under its own self-gravity, form a black hole, and the star just disappears from the sky? So you just look up in the sky, and one day there's a star, the next day nothing, no intervening supernova? Or is there some other signature of these failed supernovae that we can perhaps use to identify them observationally? Okay, so there was a guy, still is a guy, I thought he was dead, but he's still alive, by the name of Neutrinos, who back in 1980 realized something kind of interesting, which is that even if the supernova fails to explode, the core of the star still goes through this protoneutron star formation phase, probably, unless the star is very massive. You have these parent stability supernovae, but I'm talking about stars greater than about 10 solar masses, less than like 100-something solar masses. So you still go through this phase where the core collapses, you have this proton electron capture, you form the neutrons, and there's basically this huge nuclear reaction in the center of the star that radiates a ton of neutrinos. And so it's like 10 to the 52, 10 to the 53 ergs in neutrinos. And it ends up being, so if you do some detailed calculations of this, what you find is that there's between 0.1 and 0.5 or so solar masses worth of mass energy that are radiated in the form of these neutrinos over the duration of about a second. It's like between 1 and 10 seconds, which is the diffusion timescale for the neutrinos out of the protoneutron star. And so the vast majority of these neutrinos, so a small fraction of them can potentially get deposited in the shock front, right? That's this neutrino heating revival mechanism. But the vast majority of them just stream out through the star, don't interact with anything because they have such a small cross-section. And then that correspondingly generates a reduction in the gravitational field, right? Gravitational field is just dm over r squared, so if you reduce m, the mass contained within r, you create a time-dependent gravitational field, which will correspondingly have some influence on the overlying stellar envelope. And so Neutrinos, he did the first hydro simulations of this, and he found something really interesting, which is that from this neutrino mass loss mechanism, what you tend to do is you launch a pressure wave from the inner regions of the star that travels out to the surface, forms a shock, and erupts through the photosphere, and would give some indication, observational indication, of one of these failed supernovae. And so this all precedes the collapse and the formation of the black hole, and really it would give us some indication of the fact that a black hole has been formed, which is pretty neat. And so this is his plot from his paper that I think he hand drew. So on the x-axis, he's plotting the log of the mass contained within r, which you can just think of as basically the radius in the star. And then on the y-axis, he's showing the velocity normalized by the sound speed, I believe. Central sound speed, that is. And so at t equals 0, there's no velocity here, right? That's because the outer parts of the star are previously in hydrostatic equilibrium. But then at t equals 0, you change the mass, right? You radiate these neutrinos, you generate some time-dependent gravitational field, and correspondingly that generates these velocity profiles at these different times. And so what you can see is that you generate this little like pulse of a velocity profile that kind of travels out into the overlying stellar envelope. And at later times, particularly when it nears the stellar surface, you can see that this velocity profile goes from being this smooth little bump to something that's basically discontinuous here, which signifies the formation of this shock. This shock then continues to propagate down the density profile of the star, and eventually it just travels out through the photosphere. Okay. Which is kind of neat. And so since then, other people have done some simulations of this. So Stan Woosley and Elizabeth Lovegrove kind of did better simulations and looked at how this process works in red supergiant progenitors. There's another paper by Anthony Perot who was looking at if you form this shock, how does it propagate out and what sort of light curve do you get? But Stan Woosley and his grad student Elizabeth Lovegrove found similar things, right? You launch this wave from the inner regions of the star, carries with it around 10 to the 47 ergs, so it's definitely subluminous, or subenergetic rather, in comparison to a standard supernova, but nonetheless, this creates a sort of mild-ish explosion that erupts from the surface of the star and gives you some indication of the impending disappearance of the star in one of these failed supernovae. Okay, so there were like really two papers on this, aside from Neutron's original paper up until this year, where Woosley had a companion paper where they did more detailed modeling of the light curves from these events, and I think some of the spectra that you would expect. Okay, so Elliot and I kind of thought about this for a little bit, looked at like the couple of papers that were on this in the literature, and we had like a few kind of remaining questions that we didn't really know the answer to. And kind of the most basic one, and the one that I really wanted to understand, was what actually gives rise to the launching of this wave. Because if you like reduce the mass of the Earth by like 10%, it's not immediately obvious to me that you're going to form shocks all over the place in the Earth's atmosphere, right? And so just like a basic physical model or understanding as to what gives rise to this wave wasn't really, I mean, people had done simulations of this and definitely a conversion of the fact that you form this wave, but a really detailed analytical prescription for how this process works wasn't really provided. Where does the shock form in the atmosphere of the star? Would be really interesting to know if you could predict that, because that tells you the amount of mass and the amount of energy, the amount of binding energy that the star has above that point. So that tells you the velocity, the escape velocity of the material. It also sets the optical depth, which gives you the photon diffusion time, which tells you something about the light curve, how the light curve is going to appear. The amount of energy that's contained in this wave that you launch. So people have found that the shock carries with it 10 to the 47 ergs. But where does that number come from? How is it related to the amount of mass that you lose in neutrinos, for example? And then finally, how does all this stuff depend on the properties of the star that's undergoing this failed supernova? Is this 10 to the 47 ergs, is that just kind of a universal number, or does that change depending on the density profile of the star, for example? So these sorts of questions. And so this was kind of the start of this project, and this is what we tried to answer, and so this is going to be the main focus of my talk today. So let's go back to the beginning and try to understand, we want just a phenomenological model for what we think gives rise to this wave launching and steepening and shock formation. So what's the basic understanding? What do we think is going on here? Okay, so the neutrinos, right? We go back to the beginning, form this protoneutron star, radiate these neutrinos. They all leave through the stellar envelope, don't really interact with anything, and they take with them 0.1 to 0.5 solar masses. That loss of mass corresponds to a reduction in the gravitational field. Okay, so Neutrinos realized this. It's a pretty cool idea. And the important part is that the overlying stellar envelope was previously in hydrostatic equilibrium with the mass that used to be there. Okay, so if you remove the mass, suddenly the star is kind of overpressured, you can think about, and that causes it to expand. So you generate some motion from the reduction in the gravitational field. Okay, so what motion specifically do you impart to the envelope from this loss of mass? So you can show from the equation, from the radial momentum equation, actually, that the motion initially exhibited by the envelope, by the stellar atmosphere, photosphere, and everything up to the core, is actually really simple. It's just the acceleration times the time is what you get for the initial expansion of the stellar envelope. Where the acceleration here is just g delta m over r squared. Right? Delta m is the mass loss, g Newton's constant, 1 over r squared. This is just basically the net gravitational field that the star experiences times time. And so everywhere, initially, you get this expansion phase where the motion is purely dynamic. And so what I mean by that is that if you go back to the momentum equation, you completely ignore the pressure gradients. This is the expression that you get for the radial velocity. You just assume that the mass loss occurs impulsively, right? Which is very simple, which is nice. Okay, but there's a problem with this, which is that the inner regions of the star, interior to which you contain about 2.5 solar masses, because that's the amount of mass you need to form the neutron star, all that stuff is falling into the center of the star and forming this protoneutron star. Okay, and you have to maintain this additional part of the motion, because if you don't, then you don't actually have the accretion. You're not forming the protoneutron star. You don't have the neutrino emission, and you're not generating the time-dependent gravitational field. Okay, so you need to have this, or otherwise the whole problem doesn't really even make sense. And so what this means, this contradicts the fact that the entire envelope wants to expand. Right? You have this infalling region. Overlying on top of that, you have this region that wants to expand in the reduced gravitational field. So how do you reconcile these two distinct phases of motion? And so what this does, this is basically a boundary condition that you need to enforce in the interior of the star that you cause things to fall in. And what this does is it basically gives you a second phase of the motion that in this case is pressure mediated. And so essentially what happens is you have a pressure wave that carries out information to the overlying stellar envelope that tells the outer parts of the star that the inner region is falling in. And that sort of halts the expansion and tells the envelope that actually there's a boundary condition in there. This is very mathematical, but there's something going on in the interior, right? You have to turn around and come back in and accrete. In some sense, you sort of have to obtain some new sort of hydrostatic equilibrium in the reduced gravitational field. Okay? So as this wave propagates out, it then steepens near the stellar surface as it runs down the density gradient. You form a shock that erupts through the surface, and that gives you this observational indication of the failed supernova. Okay? So that's sort of like the basic phenomenological picture that we kind of came up with, is that you have this like two-phase motion, this initial dynamic expansion that's followed by this pressure-mediated response where the star tries to come into some new hydrostatic equilibrium with the fact that the center is falling in. So it's not really hydrostatic, but you get the idea. Okay, so that was sort of our kind of the idea. That's obviously substantiated by the simulations, and so what we wanted to do was come up with some sort of a mathematical model, fairly simple model, to try to kind of substantiate this understanding and see if we were kind of on the right track. And so the way you can do this is to note that the mass that you lose to neutrinos is always a fairly small fraction of the mass contained within any radius r, right? Because the mass of the neutron star is 2.5 solar masses. So even if you lose 0.5 solar masses, that's still at most 20% of the total mass contained within any radius r. So you can treat that as a perturbation, and then correspondingly that generates a perturbation to the gravitational field, which we already know, right? G delta m over r squared. That generates a perturbed velocity profile, which generates a perturbed density profile, which in turn generates a perturbation to the gravitational field due to self-gravity. And so all of these things are coupled through a system, through the continuity, the momentum equation, the Poisson equation. So what you can do is a bunch of math. And what you find is that you generate a fundamental equation for the radial velocity that you impart to the star as a combination of these dynamical effects and the pressure-mediated response. And so it looks basically like a wave equation. You can think of omega as your Fourier transform variable. The radial velocity here is the Fourier transform of the velocity. L here is just some linear operator. And then the right-hand side of this is some messy function, but ultimately it's proportional to delta m, this mass loss, which is the perturbation. Okay, so that like seeds the perturbations. And so the way to solve this is you can construct the eigenmodes of this linear operator. You can expand the velocity in terms of that. And by knowing the right-hand side, you can solve for the coefficients. It's all pretty straightforward. It took me a while to figure out that that's what you're supposed to do, but it's straightforward once you know that that's what you should do. And so it turns out to be really nice because you can, by following this route, you can find really general solutions to this problem. And so basically, for any star for which you can construct the eigenmodes, so pretty much any well-behaved star, you can construct the solution, and you can solve for all of these interesting variables, the velocity, the density, the energy, and everything contained within the star that is this response to the mass loss. So it's nice that it's so general, but it's kind of a double-edged sword because it's very general, but you can't actually make any plots unless you actually specify the pressure and the density profile. And so what we did was to sort of see if we got anything that looked like anything that resembled the Neudosian's hand-drawn plot, and also some of the more recent work by Stan Woosley and Elizabeth Lovegrove, was we applied this model to the simplest possible star we could think of, which is just a polytrope. Okay, so P goes like rho to the gamma, where gamma is a constant, so you have constant entropy. So a very simple star to see what we found. To see if what we found was close to right. Okay, so this plot, this movie, is going to illustrate what the velocity does. And so I picked I think gamma equals 1.5 polytrope, and then I matched the properties of that polytrope to the sun. So the polytrope has a solar radius and a solar mass. And so on the x-axis here, I'm plotting radius, distance from the center of the star in units of centimeters. The velocity in centimeters per second is on the y-axis. So the sound speed, the center of the star is like a few hundred kilometers per second, so a few times 10 to the 7. And at t equals 0, right, the envelope of the star is in hydrostatic equilibrium, just like the Neutrinos, right? There's no velocity here. But then at t equals 0, I decrease the mass contained within the forming protoneutron star, and I let it go and I see what happens. So what you can see, so through this linear perturbation theory, is that we actually get something that looks pretty similar to what the Neutrinos had, which is good. Right? So we get this, at early times, we get this kind of like peak here that propagates out, doesn't really do too much, it stays very subsonic. But then eventually, as it nears the stellar surface, you find this nearly discontinuous spike in the velocity profile. So this looks a lot like very similar to what the Neutrinos had, which is great. And so what I'm trying to say, what I'm trying to motivate, is that at each one of these points where I've just kind of frozen what the velocity profile looks like, what this should be, if our understanding of this is correct, is that out exterior to this is falling off basically as 1 over r squared. So the velocity is doing this initial dynamic expansion phase. But then you have this point where the sound, there's been some conveyance to the outer parts of the star by the sound speed, that the inner parts are doing something different, and that causes the outward moving atmosphere or envelope of the star to stop expanding and do something completely different and join on to the inner regions of the flow. And so this plot kind of substantiates this a little bit. So it's the exact same thing that I showed before, where I just renormalized the y-axis to be velocity normalized by the central sound speed. And then this is just radius normalized by the radius of the star. And so this is for very early times. So tau equals 1 here corresponds to 6 minutes from the previous movie. Remember, it took 45 minutes for the thing to get all the way out there. So this is very early on in the evolution. So the curves here are just showing the velocity profiles that you induce from this mass loss. The dashed curves are showing the 1 over r squared prediction from the dynamic expansion phase. And then the points are showing, on the x-axis, the distance out to which a sound pulse would have traveled in the time tau. So basically, yeah, you're just integrating dr over cs, solving for that as a function of time. And then the value of the y-axis here is just set by the dynamic value, so just delta m times t over r squared. And so what you can see is that for radii exterior to this point, things fall off almost exactly as 1 over r squared. is kind of cool. Right? You actually recover this 1 over r squared dependence. And then interior to that, you again get this matching on to the inner boundary condition. And you also see, like at later times, so the peak here, or the peak in this velocity profile still corresponds to where the sound pulse has made it to, right? Like these two lie on the same vertical line. But the value of the velocity here is slightly higher than you would predict from this dynamic expansion. And the reason for that is that the gravitational field has this 1 over r squared dependence. And so what that means is that shells at slightly smaller radii are accelerating slightly faster than those at larger radii. And so that differential acceleration causes a compression of the gas that generates an additional pressure gradient that develops over roughly 1 center crossing time that then further accelerates the flow. And so for that reason, you get a slightly increased velocity here at later times. Okay? This is cool, right? So it really seems like this is what's going on here. You get this sound pulse that's launched from some inner radius. Near the surface of the star, this pulse steepens, and eventually you approach this Mach 1 region. And so sort of a downfall of this linear perturbation theory is that by assumption we neglect the nonlinear terms, right? And so realistically what you expect to happen is that as the flow approaches Mach 1, the outer parts of the star can't respond fast enough. The stuff kind of catches up to itself, and you should form this shock, as other people have seen in their simulations. But in this perturbation theory, what happens is the pulse just kind of reflects off the surface, and the entire polytrope just sort of oscillates around. And so you can make a funny movie of this. So at t equals 0, again, I'm just going to reduce the mass contained in the center. And what you can see is that there's this kind of pulse going out. The envelope is responding dynamically and also hydrodynamically. And then eventually the entire thing just kind of pulsates and rattles around and doesn't really do anything. Right? So there's no shock or anything like that that forms here, even though you expect realistically that there should have been one. Right? So there's like these very long time scale oscillations that are basically just stellar pulsation modes. And so what we did, so since you expect these shocks to form when the Mach number approaches 1, Dan Kaysen has a pretty simple little 1D hydrocode that we used to sort of compare and see how good this analytic prescription, this simple perturbation analysis is to the full nonlinear problem. And so this plot here just shows on the y-axis the Mach number, so the velocity normalized by the local sound speed. That's as a function of r in centimeters, and so this is exactly the same setup that I showed before, where we have this polytrope reducing the mass, seeing how things respond. And so the solid curves show the prediction from the linear perturbation theory, and then the dash curves give Dan Kaysen's, the results from Dan Kaysen's hydrocode. And so what you can see is that at early times, when you have very subsonic flow, the two are virtually indistinguishable. But then at later times, as you approach Mach 1, you can see that Dan Kaysen's code has predicted that this thing should actually form a shock, right? Whereas the analytical solution just kind of happily goes on, not really doing anything too interesting. But so this is pretty neat, right? Because you can, ultimately what you can do is you can use this linear perturbation theory to predict where the shock is going to form. Because even at Mach 0.2, 0.3, these are really not all that different, right? They're actually fairly similar in terms of amplitude. They're off a little bit by the distance, but okay. So at some point, this pulse steepens into a shock. You'll deposit some energy. And so one of the questions that we wanted to know the answer to was how much energy you actually deposit at that point. And so you can actually estimate kind of heuristically what the energy is contained in this sound pulse as it propagates out. And so if you remember, so the star is approximately expanding dynamically initially. And so originally, you get some velocity profile that's just g delta L over r squared times tau of r, where tau of r is this time taken for the sound pulse to reach radius r. So everything will accelerate dynamically until the sound pulse reaches you. And when the sound pulse reaches you, it tells you to turn around and come back and basically slow down and reach some new equilibrium if you can. So what that means is that the sound pulse is kind of like you can imagine like collecting the energy of the outgoing stuff as it propagates, and that causes the sound pulse energy amplitude to grow as it's kind of removing the kinetic energy of the outflowing gas. And so you can use this to just write down an approximate expression for what you think the energy should be. And what you find is that the energy in this sound pulse should be something like g delta m squared over alpha. G is Newton's constant, delta m again is the mass loss of neutrinos, and alpha is the pressure scale height, so proportional to the, pressure scale height at the inner region where material is falling onto the protoneutron star. And so what's cool about this is that if you put in numbers here, you get around 10 to the 47 ergs, which is in good agreement with what people have found in the past. And so this is kind of a messy plot, but it's just showing, just kind of validating this estimate. So there are 3 different components to the energy contained in this outgoing sound pulse that propagates out. You have the kinetic energy, which is the usual 1/2 rho v squared. The internal energy, which is the correction to the pressure that you induce. And then the self-gravity energy correction, which are just given by these 3 curves here. And then the total, the combined, is given by the red curve here. And so this is shown as, this is the energy as a function of time. And so as the pulse goes out, this is sort of what you're estimating here, the total energy contained in the thing, right? So it grows as it's sort of telling the rest of the envelope to stop expanding. And then this dash curve here just gives the analytic prediction, this thing that I showed before, where you can estimate it from this integral. And these estimates agree pretty well. And so it really suggests that you can actually self-consistently, through this linear perturbation theory, really estimate the amount of energy that goes into this pulse and eventually steepens into this shock and erupts from the surface. The purple curve here is kind of confusing. It's the total energy contained in the star. So instead of just integrating over the width of this pulse, if you estimate the total amount of energy that this mass loss is deposited, you get a slightly bigger number. So like 3 times this little 10 to the 47 ergs. And I think that's because as the pulse propagates out, it's not getting all the velocity that's trying to dissipate. Some of that is going into the new equilibrium configuration and increasing the pressure of the star. And so you get a slightly increased value for the total energy deposited into the star. But overall, these agree pretty well. So this has all been great. All this stuff seems to work for polytropes. But real stars aren't polytropes. Right? They're typically a little bit more complex than that. So how does this, a good question is, how does this all extend over to real stars and other progenitors? For example, ones that you could generate from MESA. So in principle, you can do all the same analysis that I already did. As I said before, right, the solutions that we found are really general. So in principle, you can just construct the eigenmodes of whatever MESA solid progenitor you want, apply all this formalism, compute the coupling coefficients, derive the time-dependent, space-dependent perturbations, and all this stuff. And you could do that. It would take probably about as much time as it would to just run a simple 1D vector code. But what you can also do, and you can show this kind of rigorously, is that the energy, or the wave power, which is kind of the energy advected by this sound wave as it propagates out, is approximately conserved. And so you can show this a couple of different ways. You can show this through the eigenmode decomposition, and also, a number of other ways. And this is approximately conserved as this wave propagates out. This LW is approximately a constant. And so that's what I'm showing here. So you have the different solid curves here showing the velocity profile, the same thing that I've already shown. The black curve here is showing the density profile of the polytrope, scaled by a factor of 5, just so that you can see it and it's not all down here and muddled with everything else. And then the dashed blue curve is showing the solution that you would predict for the growth of the velocity profile if you assume that this wave power is conserved. And so what you can see is that they actually do agree pretty well, right? There's like a little bit of a discrepancy here, but especially towards the surface, the growth of these things are almost identical. And so this conservation, this wave power, holds pretty generally, right? It doesn't depend on the specific properties of the star. As long as you know the density profile and the sound speed, you can construct what the solution for the velocity should be. And so what you can do then is use this to get a basic understanding of the growth of the Mach number of the flow throughout any kind of general arbitrary star, not necessarily just a polytrope. And so So in collaboration with Rodrigo, Rodrigo ran a whole suite of simulations. I should have put a reference to his paper, but so there's a companion paper out to the one that we posted where he extended some of the work of Elizabeth Lovegrove and Sam Woosley and looked at this neutrino mass loss mechanism for a wide variety of stellar progenitors, including Wolf-Rayet stars, yellow supergiants, blue supergiants, to see how the energy and everything, doing the full numerical simulations, how those things differ as a function of progenitor. And so what these solid lines are showing here is the Mach number, again as a function of R, for one of the Wolf-Rayet stars that he analyzed. And so it's like a 40 solar mass, zero-age main sequence Wolf-Rayet star that lost a lot of mass in stellar winds. And then again, this mass loss occurs. So what kind of sound wave, what kind of shock waves do you generate? And so the different curves here are just at different times. And so you see, similar to what the Lovegrove and Woosley simulations and the Doijian simulations showed, is that you get the growth of this, this velocity profile as it propagates out into the Wolf-Rayet, eventually steepens, forms a shock. And so then what this dash curve is showing is the solution that you get, again, just assume that this wave power is approximately conserved. And so the two agree very well at early phases. It really tracks the linear growth of this Mach number. But then near the surface, they start to disagree a little bit. But what you can see is that this assumption really does give a very good estimate of where you think this shock is going to form in the atmosphere or the envelope of the star. Okay. So my last couple slides, just wanted to talk about something that I don't think anyone has actually predicted before from this mechanism, which is that you can actually get two shocks from this. So if you recall from this dynamic expansion phase, I said that, yeah.
Sorry, before you go on with this, just curious, the conservation of energy thing, is that true even when it steepens into a shock, into wave energy?
I don't think so. I think then you want to use something more like a Sedov-Taylor type of approximation for the conservation of the energy across the shock front. Although even that is a little tricky because you get to what tends to happen is the wave steepens into a shock, and if you then follow the propagation of the shock, which is what Rodrigo's done with Flash, you don't ever actually, at least for some cases, especially for the red supergiants, you don't really get much above Mach 1. And so you kind of saturate there for a while, and so it's not really clear, so it's not really like you're in the strong shock limit. And so there's some interesting balance between the gravitational field, where the gravitational field probably isn't all that ignorable in these cases. And so that's definitely an interesting, completely separate aspect of this. But yeah. All right, so I'll just finish by saying, right, so interestingly, you can actually get two shocks in this system, or from this mechanism. So if you recall that the initial expansion is this roughly dynamical thing, and as I already argued before, what this means is that shells at smaller radii accelerate slightly faster than those at larger radii. And so for the very outer parts of the star, where it takes a long time for the sound wave to propagate out and tell them to stop expanding, you can actually encounter situations where inner shells catch up and overcome shells at larger radii, right? And so in a nonlinear theory, that would produce shell crossing and shock. And so what we found is that this actually does happen for polytropes. You saw in the movie that I showed a while ago, it's kind of difficult to see, but this does actually happen near the surface of the star. You see shells of slightly smaller radii overcome those, and then they shoot back in and do a bunch of things that the linear theory isn't capturing correctly. And that's just because the sound speed at a polytrope, by definition, goes to 0 at the surface. So there's a finite sound travel time, but the sound speed itself goes to 0. And so that means that the shells at large radii have a really long time to accelerate and catch up to one another. For a real star, this won't necessarily be true because, as you saw, one of the big differences between the numerical simulations and the analytical predictions is that the sound pulse accelerates faster as basically the sound speed evolves. The shells kind of catch up to each other even more quickly and take over one another. And so what this sort of suggests is that what might happen is you actually sort of take over this outer shock that's trying to build by this inner shock. And so if I just go back to this plot from Rodrigo's paper, you can see that this is sort of starting to build up here. You're getting this Mach number close to 1 region out here where shells are catching up to one another. But like the next time step here, this shock just completely overwhelms the thing and takes it over. And so one important caveat is that in Rodrigo simulations, it's very difficult to resolve the surface for the scale height. And so this still might occur, but you need to do some higher resolution simulations, which I think you might plan on doing. We talked about this a little bit with Elliot. And that could have important observational implications if you have, I don't know, it's kind of a weird situation where you have like one shock running into another shock. Could be interesting, sort of have to see. And so I'll just summarize. This neutrino mass loss generates some pretty interesting physics. You get these two phases of evolution where you have this initial dynamic expansion of the envelope followed by this pressure-mediated response, and that pressure-mediated response generates this, this wave that eventually steepens into a shock near the stellar surface. And so using this perturbation theory, we can really nail down a lot of interesting aspects of this and show what the energy is that's in this wave as it transforms into a shock, where you can then use something more like a Sedov-Taylor approach or something analogous to try to understand the shock propagation. And you can use this potentially in conjunction with simulations to try to understand the later phases of this and try to calculate the light curve as the shock breaks out, which some people have done. So that's it. So I'll take any questions if you guys have it. Slide is for Dan. Yep.
Is there any limitations on the density profile that you use? You use just polytropes, but could you plug in anything from Mesa?
Yeah, so
Okay.
I actually did try to do this for the Wolf-Rayet progenitor. And you get kind of interesting, so like near regions of different shells, you get these density or entropy jumps. And so if you want to do just a simple, second order linear operator, you get kind of bad stuff happening there. And so I think you have to like kind of smooth over those a little bit, but otherwise, yeah, you can do that.
Can you split it? Like do one analytical thing for one layer and the second
Yeah.
layer?
So this is actually so for like a red supergiant, where you have like kind of the helium core and then this like really extended, super rarefied hydrogen envelope. That's exactly the sort of thing you want to do, and that's why I think that the linear perturbation theory is nice, because you could essentially calculate how this sound pulse builds up as you approach the surface of the helium core, but the density technically doesn't go to 0, but it drops by like 8 orders of magnitude or something like that. And then you could use that as sort of a starting point in either some other formalism, so you'd want to do something like basically some analog of the some analog of the Sedov-Taylor problem, or you could put it in a code and see how the shock actually propagates down the envelope.
So what would we actually observe from these things? Is it just like a very weak flux supernova, or is it something else?
Yeah, so when the shock actually breaks out, depending on the star, so for like the Wolf-Rayet star, it gets to be really, really bright because you have a fairly small amount of mass there and you just dump all this energy into it. So you get this really abrupt burst. And then at later phases, hydrogen recombination gives you a longer lasting, redder transient that can last from like a week to a month. And so this was part of what Tony Perot and Lovegrove and Woosley did in their later papers, was to actually try to calculate what these things look like.
I was going to ask essentially the same question about the changing group. What are the chances of observing
Yeah.
the neutrinos?
Oh, the neutrinos.
Have you done any calculation? Granted, there are great uncertainties
Yeah.
in all sorts of aspects. But I wonder if you gave any thought to it.
I haven't thought about that aspect of the problem personally.
It has to be close, right? We know that from 1987A. Like you can see in the neutrinos that the supernova has to be really close.
Yeah.
Like,
I was wondering
no,
just what, there's got a lot of neutrinos here.
Yeah.
How far out could you move?
Yeah. Well, I mean, so one thing is,
Fraction of stars.
Yeah.
that might-
I mean, so if you can, so since these, so luminosity you get from these are like 10 to the 41 ergs per second or so, and so those have to be fairly close by in the first place in order to be able to see them. And so that actually, I mean, yeah, that'd be great, right? If you could actually see the outburst and then see the neutrinos in addition, you'd really have a good idea that you know what physically is going on, which would be really neat. But yeah, I can't say, I personally can't come up with a good estimate on the top of my head. But,
So, in this neutrino capture mechanism, you want the neutrinos to be captured in the post-shock gas, the dense gas following the shock, is that correct?
well, that's like the neutrino heating mechanism, yeah.
Heating mechanism.
Yeah, but I'm saying that, like, so yeah, so that occurs for like 1% or so of the neutrinos that are radiated. And so 99% or more just stream out and they take with them this mass.
And so then, following James's question, so if you had a density profile of the star, then would there be a restriction on this mechanism depending on the density profile? Say, for example, if the gas were denser at the center of the star than at the shock.
Yeah, yeah. I mean, if you, yes. So this has kind of been taken into account in some more detailed models of how the neutrino mass loss proceeds. I mean, really, what you want to do is you want to take into account how the mass of the core is evolving as stuff falls in, and then use that with some fairly simple prescription for the evolution of the protoneutron star and the neutrino emission to kind of self-consistently do that. And so depending on the stellar profile you get more or less mass radiated due to neutrinos because you have more or less time before you exceed the Tolman-Oppenheimer-Volkoff limit for the mass for the neutron star and stuff. Yeah.
Kind of a related question. So if you require that the shock does, that the wave does steepen into a shock before it reaches the edge of the star, does that give you like strict criteria on the type of stars this phenomenon occurring?
So I think the only ones where it doesn't steepen into a shock. So in the linear, right? So this is tougher to answer in the linear perturbation theory because in this linear perturbation theory, this wave power is always conserved, and so you'll always approach Mach 1. If you have a star where the density goes to 0 at the surface, if you impose some restriction about the photosphere, then yeah, absolutely. Like if you wanted to steepen into a shock before reaching the photosphere, then yeah, you could put some restrictions on the type of star. And I think the only ones for which that didn't happen, most of the ones that Rodrigo looked at formed shocks near the photosphere. There might have been, like, I think the yellow supergiants were very, very weak. And so those cases, there could actually be a significant amount that actually gets reflected, which could have some interesting, I mean, I guess what's really going to happen is that then the entire star is just going to get eaten by the black hole. And so it's not really going to look like much other than just a disappearing star. But yeah, definitely different stars give rise to different, so the energy is the same, but since the density profiles are different, you get a different looking light curve out of some of them.
I have a general question about like this. You keep saying different types of stars, but it seems like we have models. So are we thinking about stars of different mass or different evolutionary stages, or what says?
Yeah. Yes. So different. So depending on the star, you get it's more or less simple to blow up, right? Via a supernova, standard supernova mechanisms.
Right. Yes, I'm wondering what is this underlying? You said it's a compactness, but what sets it? Like, if you chose parameters to put into MESA, how would you like create those different progenitors?
I mean, I think people have sort of looked at this in a fair amount of detail. I'm not sure off the top of my head though what the so what zero age main sequence and what I'm not entirely sure.
It would be interesting, like, to know that you could kind of predict then how many of these you would expect with respect to the regular supernova.
Yeah.
I don't know how, sorry, I don't know how different it is now at MESA, but I mean, in past stellar grids, it's usually mass and metallicity as a basic parameter set, and then their metallicity is also kind of maybe a real parameter, but also kind of a proxy for uncertainties and semi-convection and other things, where you see low metallicity, you get blue supergiants, and high metallicity, you get red supergiants, at least at a basic way of how to tell what stars.
Yeah, right, so your solutions seem general to any type of spherically symmetric problem where you have this boundary condition. It's a mass loss, right? So is the boundary condition just that you have some radius where there's zero velocity?
Yeah, so that's like a subtle little technical point. So you can do, so the solutions that I showed were having zero velocity there. In reality, you want to have infall, and so you can do that in this problem. It just gets to be a little bit trickier, and it generates slightly longer equations. And so for the paper, in this presentation, I just focused on the case where you set the velocity to zero. But ideally, yeah, you want to have some infall, and that changes the solutions a little bit qualitatively, but really not too much quantitatively. But yeah, that's ultimately what sets it. Yeah.
And then, okay, and so I guess then there's a range, similar to every question I think that's been asked, there's a range of certain types of stars where that would be true, right? I guess maybe just elucidate for me again when this is just all, works for all types of...
Yeah, I mean, I guess it's once you lose pressure support, stuff starts falling in, and then once you enclose enough mass to form the protoneutron star, that's when you start to form this collapse, and that sort of sets the radius at which you want to now kind of impose this boundary condition, right?
Sure, what if we have like a 250 solar mass star though?
Yeah, which probably might do something completely different, who knows? But yeah, I think.
So can you say anything, just given the outputs of these sims, what the resulting fallback signal that would be affected by what happened in the envelope when the shock passed through it?
Yeah, so Rodrigo has looked at this, and you get sort of like the same, it's very similar to what like older calculations by like Chevalier back in the 80s had found from like the same, well I guess it's not the same thing, but a similar thing for the neutron star, pushing on to the neutron star. Yeah, so like at later stages, you might have some tail of stuff that falls back at very late times, and I think would give you something that looks almost like a t to the minus 5/3 type of fallback onto the thing. So if you had enough angular momentum or something, you could form a disk, and that might look qualitatively similar to a tidal disruption event, maybe.
Yeah, I guess my question was, since the shock runs out,
Yeah.
the wave runs out through the envelope, that's altering the density profile in some,
Oh, the density, yeah.
in some way. And does that could imprint itself on the fallback signal in some noticeable way?
I mean, I think that the density perturbations are typically aren't that big until you get out to like where the shock actually forms. Right. At which point you have a fairly small amount of mass. So yeah, it's possible.
Not at the very late times.
Yeah.
All right, let's thank Eric again.
The number of so-called failed.
Yeah.
Smiles a lot. Blurry vocal.
Yeah.
What's that ratio?
I don't either. I mean, I think the thing that really seems to determine it, I mean, obviously it would be nice if we had a full working model of what ultimately drives the supernova in the first place. But I think the real thing that sets it is this density, this like compactness ratio. And so stars with, so I think it's like if you have stars in the range of like, I think it's like 10 to like 20 solar masses that have standard metallicities to form like red supergiants. I think those are the ones that are very difficult to make explode. So like what fraction of those end up from the IMF? Yeah, that's a great question. I'm not, somebody else had, so I gave a very, yeah, I agree, yeah, I gave like a really condensed version of this talk at the Einstein Symposium a few weeks ago, and somebody else asked that.
And in between,
yeah, I forgot about that. Yeah. Done.
Oh, well.
Yeah. Oh, yeah. Next time. I'll be back.
Still some work to be done.
We're very hard at imaging the calibrated ones. But those ones are observed for less time.
more fun given the set diagram.
She said to be there.
Arguing in the science area, see down. I don't know.
He's also asking
Are you back at work?
I think we're okay.